Hello everyone. In this video, I'm going to present a method to quantify impairment or disease severity using artificial intelligence models that are trained only on healthy people. The insight underlying our method is that these models tend to lose confidence when we apply them on patients that are impaired or have a disease. This enables us to use this loss in confidence to perform anomaly detection, which in machine learning is what we call the problem of identifying individuals that depart from a reference population. In this case, those individuals are impaired or have a certain disease. We call our method COBRA, for confidence-based characterization of anomalies, and we're interested in the medical domain, which is why our mascot is this cobra snake that you see on the left, which is dressed like a doctor. All right, so let's take a look at what the plan is for the video. First, I'm going to present our main motivating clinical application, which is measurement of stroke impairment. Then I will describe our method for confidence-based anomaly quantification. Then I'm going to illustrate the broad applicability of the proposed method by talking about a completely different medical condition, which is knee osteoarthritis. And then I will finish with some concluding remarks and also a word of caution. So let's start talking about stroke. Stroke is caused by lack of blood flow or bleeding in the brain. Around 800,000 people suffer from stroke every year in the United States. So as you can see, it's really a big deal. And unfortunately, a lot of those patients are impaired, have their movements impaired due to the stroke. Stroke is one of the leading causes of serious long-term disability. In fact, stroke reduces mobility in more than half of stroke survivors age 65 or older. Our goal here is to address a key challenge in stroke treatment and rehabilitation, which is quantifying how impaired a stroke survivor is. So let's take a look at how this is quantified currently. Currently, the way we quantify to what extent a stroke patient is impaired is through what is called the Fugl-Meyer assessment or similar assessments, where a trained expert, which we see here on the left, of course she moved the moment I marked her, asks the patient to perform some simple exercises. You can see she has a notepad here. So the way this works is she will ask the patient to perform some simple exercises that are related to each of the joints in the upper extremities, and she will score to what extent the patient is able to perform those movements or not. So for each of them, the patient will get a 0 if they cannot perform, a 1 if they perform partially, and a 2 if they perform fully. And then you just add up all those scores. So a patient that is perfectly healthy will get a score of 66. A patient that has some degree of impairment will get a lower score. And the lower the score, the more impaired the patient is. So here they're looking at shoulder. Oops, sorry about that. Let's take a look at, here they're looking at the shoulder again. Here they're looking at the thumb, coordination, and so on and so forth. So the point I want to make here is that this actually takes a while. And it requires a trained expert to actually sit with the patient and go through all of these motions and write everything down. So current assessment is time consuming and requires an expert. Our goal is to perform automatic quantification of impairment exclusively from video or wearable sensor data. So we just need a video of the patient or for the patient to wear some wearable sensors. And if this is achieved, it could enable continuous monitoring that is objective and affordable, which would enable doctors to adjust treatment of patients more granularly, and also for patients to know what progress they are making during rehabilitation. Here is the data that we plan to use, well, that we use in this study, I mean. The video is pretty straightforward, right? So the video would look something like this, as I have marked on the right. And on the left, what we see, so if you look carefully at the video, you will see that the patient is wearing some wearable sensors. And here what we see on the left is the output of those wearable sensors, which correspond to different types of angles and accelerations of the sensors. So when I'm talking about wearable sensor data, I mean a time series of roughly 100 values that change over time that capture the angles and accelerations of sensors worn by the patient. And again, we want to be able to quantify the impairment of the patient directly from this video data or from the wearable sensor data. So here we run into a problem. If you know about machine learning, you might be thinking, well, this is easy, right? I'm going to gather, I don't know, thousands of patients. I'm going to keep track of how impaired they are, and I'm going to train a big deep neural network to estimate impairment. That would be awesome if we could do that, but unfortunately, no such data set exists. The largest available data set that has a score of impairment for each patient and then some wearable sensor or video data only has 51 patients. It's just incredibly difficult to gather these large-scale databases of these patients where impairment is actually measured. And this is not a problem that is unique to stroke. There are many medical conditions where it is very difficult to gather these large-scale databases. So the available data set is too small to train and evaluate a machine learning model. In order to address this, our proposed solution, is to use a model that is trained only on a healthy population, but then can be applied to stroke patients to quantify their deviation from normal motion. And this brings us to our proposed method for confidence-based anomaly quantification. So anomaly detection and quantification is the problem of identifying data points that differ from a reference population. And the reason why I also have quantification there is because we're really interested in quantifying to what extent they deviate. In our application to stroke, this would be patients who do not have normal motion because of impairment. So they deviate from the normal motion of the healthy subjects. Our method, which is called confidence-based characterization of anomalies, or COBRA, consists of two steps. First, we train a machine learning model or an AI model to perform a clinically relevant task. For example, identifying motion. I will go into this clinically relevant task for our stroke application in a moment. The model is trained exclusively on a healthy population. And then the second step is to apply this model on the patients of interest and use the model confidence to perform anomaly quantification. The idea here is that if the model is trained on the healthy population, for example, to identify motion, when it encounters abnormal motion because the patients are impaired, then its confidence is going to drop. You didn't see that. Its confidence is going to drop. And we can use that, we can exploit that to quantify to what extent the motion is abnormal. We're going to see this in much more detail in a moment. Okay, so what do I mean by identifying motion? We're going to focus on motions that are carried out in a rehabilitation setting. You might have noticed that I don't really know how to pronounce rehabilitation. I hope that's more or less okay. So during rehabilitation, stroke patients perform different activities. For example, dressing, bathing, meal preparation. These are activities that are useful for them in their daily lives. Those activities are typically composed of different functional movements. For example, cutting vegetables, tasting sauce, or stirring a pot. In turn, we can separate any such functional movement into 5 functional primitives, okay, which are always the same. These are reach, reposition, transport, stabilize, and idle. And this is what we're going to train a machine learning model to identify. Let's take a look at what each of these fundamental functional primitives look like, because these are the movements that are going to be detected by the machine learning models that then we're going to use to quantify impairment. This is a reach, where the patient is is reaching out to touch an object. In this video, I want you to focus on the left arm of the patient, which is the impaired one, and you will see that the patient transports an object, and that first part of the movement is what we call a transport. And now the second part of the movement, when the patient retrieves this impaired arm after transporting the object, when they move it back, that's called a reposition, and that's a different type of fundamental movement. Okay, and now the fourth type of movement, which is not really a movement, and I want you to remember this. The 3 first movements, the patient actually moved the arm that is impaired, or paretic arm, as it's called in stroke rehabilitation lingo. Here, the patient is just stabilizing an object without really moving it while they do some stuff with the other hand, okay? That we call stabilize. And finally, the last type of fundamental motion is idle, which is really easy. Here, again, we have to focus on the paretic arm. The paretic arm is not really doing anything. Okay, it's just not doing nothing. We call that idle. Okay, so we have previously developed machine learning models that are able to identify these 5 primitives that I just talked about using deep neural networks. Okay, this represents a deep neural network, typically with convolutional filters. And they do this either from wearable sensor data, which is what this diagram indicates, or from videos. Okay, now in that past work, we applied this on stroke patients to identify these movements in stroke patients. Let me show you a video of this. So in our work, basically, we trained these deep neural networks. You can see here that the paretic arm, which is of interest, is marked with this red oval. Here on the left, we're showing the prediction of our deep neural network, and on the right, the ground truth, which was labeled by a trained volunteer. Okay, and the models are quite accurate. They have trouble when the patient is really impaired because the motions are quite heterogeneous. The big difference between this past work and what we're going to do here is that we're going to train these models to identify motion in normal subjects, in healthy subjects. Okay? But we're going to use this same model that we had developed previously to identify this kind of motion in stroke patients. For our method, it's important to carefully define what we mean by confidence. So the way machine learning methods for classification typically work is that you input some data. In our case, it's going to be a segment of video or a segment of wearable sensor data. And then the model outputs probabilities corresponding to each of the classes of interest. In our case, these classes, where we want to classify the data into, are the 5 fundamental primitives that I talked about before. So in this case, maybe the hand is not moving a lot, and the model determines that this is an idle. But it produces probabilities. So it will say, oh, I think it's 10% a reach, 5% a transport, 10% a reposition. Sorry that there's a little bit delay since I draw on the iPad and you see it on the screen. 7% stabilized and 68% idle. So then when we want to identify the movement, we'll typically identify the movement using the highest probability. This highest probability also indicates how confident the model is in its prediction. And that's what we call the confidence of the model. In a way, it's how likely the model thinks that it is correct. Okay, so it kind of makes sense to use this to quantify confidence. Now let's take a look at what happens if we train these models to identify motions, and we only train them on healthy patients, and then we apply them. In this case, we're going to see what happens if we apply it to a held out test healthy subject and a patient that has impairment due to stroke. And what I'm going to plot here, what I'm going to show you here is a histogram of all the confidences over many segments of wearable sensor data. Okay? And as we will see later on, these segments are those corresponding to the 3 functional primitives that have to do with motion. I'm going to talk much more about that in a moment, so don't worry about it too much. For now, just focus on the fact that these are confidences for a healthy individual in blue and an impaired individual in red. What do we observe? We observe that in general, the model is much more confident when it classifies data coming from the healthy individual, because the healthy individual is performing normal motion in general. It's much less confident when it encounters data from the impaired individual, which has an FME score of 45, which is not super low, but it definitely means that the patient is impaired. And this is what we exploit to perform, to automatically identify and quantify impairment from this data without having trained them all on any stroke patients. So let's recap what our method is, our COBRA method. First, we train a model on healthy subjects for a clinically meaningful task. In the case of stroke, that is prediction of these functional movements of functional primitives that I talked about, these 5 primitives. And then we apply the model on different subjects that have different degrees of impairment, and we observe the model confidence. So for this patient over here, they're healthy, they're performing normal motions, the confidence model is high. That means that their impairment level is healthy. This other patient has more abnormal movement because they're mildly impaired, so the model confidence goes down a bit. And we find out in this way that there's mild impairment. And finally, this patient is quite impaired, the movements are very abnormal. Because of that, the model confidence drops even more. Okay, drops even more, and we determine that the patient is severely impaired. Going back to our previous graph, how do we aggregate all these confidences to produce a score? Very easy, we just average them. So here, the average confidence for the healthy patient is 0.811, the average confidence for the impaired patient is 0.63, which indicates, because it's much lower than the one for the healthy patient, that the patient is impaired. It's important to take the average because individual confidences, as you can see here, can be quite noisy. Now I'm going to show you our results on a completely independent test cohort with 55 new subjects that were not seen by the machine learning models. Some of those subjects are healthy, okay, they're in blue, mildly impaired, moderately impaired, and severely impaired. So here on the x-axis, we see the COBRA score, which comes out of this machine learning model that was trained on some other healthy subjects and is obtained completely automatically in under a minute. And here on the vertical axis, we see this FMA score, which takes between 30 and 45 minutes to compute and requires a trained expert to sit down with the patient. And what we observe is that there's an extremely high correlation between the expert-based FMA score and our automatic machine learning-based or AI-based COBRA score. The correlation coefficient is actually 0.814, and these confidence intervals, 95% confidence intervals, indicates that this is statistically significant. So this demonstrates that our automatic COBRA score is able to accurately quantify impairment. I mentioned before that when we're computing the COBRA score, we're using the motion primitives. If you remember, reach, transport, reposition. We're not using the non-motion primitives, which were stabilize and idle, where the hand was not moving. The reason is that a model can be very confident that an impaired patient is not moving. That is still easy to detect with high confidence. And in fact, if we were using just those two primitives to perform our COBRA score, to compute our COBRA score, then we would observe that there's actually very low correlation or relatively low correlation. Still, there is some correlation, but it's very slight between the automatic score and the FMA score. So it's important to use motion-based primitives or in general clinically relevant data to compute the COBRA score. This is what happens if we use everything, motion and non-motion primitives. The results are not bad, but they're definitely not as good as when we only use motion-based primitives. The correlation coefficient here is 0.68. Remember that if we use the motion primitives only, then we get a much higher correlation coefficient of 0.814. We get much better estimation of impairment. Now I'm going to show you, so I should have made that a little bit clearer, but the previous results were all just with wearable sensor data. Now I'm going to show you the same results where we're only using video data. Okay, video data is going into the machine learning model. The models were originally trained to identify these 5 primitives from videos on healthy patients, and then we apply them on our test cohort of 55 subjects that have this wide range of impairments. And again, what we observe is that the video-based COBRA score is actually correlated, strongly correlated with the FMA score computed using an expert. Here the correlation coefficient using an expert, computed by an expert. The correlation coefficient is 0.736, and again, we see from the 95% confidence interval that the result is statistically significant. So we're also able to quantify impairment accurately using the proposed score from video data. The same phenomenon occurs again where this works well as long as we use the motion primitives. This is what happens if we use the non-motion primitives. It's a disaster. The correlation here is not even statistically significant. And if we use everything in this case, this is actually a mistake because the results get dominated by these non-motion primitives. We get some correlation, almost 0.5, but it's not that strong. This really works out when we use the motion primitives to compute our COBRA score, and that's how we achieve this correlation coefficient with the expert-based score of 0.736. All right, so that's it for the stroke application. Now I'm going to move on to talk about a completely different medical condition, which is knee osteoarthritis. So knee osteoarthritis is a here I'm going to completely mispronounce this, but bear with me, musculoskeletal disorder. Hopefully that was more or less okay, at least you're seeing it there written down. And it's characterized by progressive loss of knee cartilage. The severity is quantified by the Kellgren-Lawrence grade, which indicates to what extent the knee is damaged by the knee osteoarthritis. Our goal is to automatically quantify to what extent a knee is damaged automatically from a magnetic resonance imaging scan. So a data modality that is completely different to the two data modalities that we had before, which were wearable sensor data and video data. So let's see how we can do this. We again apply our COBRA framework, our confidence-based characterization of anomalies framework, where we have the two steps. We train a model on healthy patient to perform a clinically relevant task. As we will see in a moment, in the case of knee osteoarthritis, the clinically relevant task is to classify what kind of tissue is in each voxel of the MR scan, of the magnetic resonance scan. And then once we have trained the machine learning model to do this on healthy patients, we apply it on patients where we don't know if the knee is healthy or not, and use the model confidence to perform anomaly quantification. I also have a diagram. The diagram for this application will come in a moment. First, let's talk very briefly about what do we mean by what clinically relevant task we use in this case. As I said a moment ago, we're going to use classification or segmentation of tissues from magnetic resonance imaging scans. So here on the left, you see the data that we use. In fact, we use 3D scans, so you're just seeing a 2D slice of the knee. And our goal, the machine learning models are going to be trained to identify what voxels contain tibia cartilage, which I believe are these guys, tibia bone, which are these guys, femur cartilage, which are here, femur bone that are here, or background, which is there. Okay, this is how we train the machine learning models whose confidence we're going to use to compute the COBRA score. And we train them only on healthy knees. When we train these models on healthy knees and apply them on a healthy individual that has this Kellgren-Lorentz index of 0, which means that they're healthy, and a patient that is affected by knee osteoarthritis, we observe again that on average, the healthy patient is in blue, and we see that they have, I don't know what happened there. Here we see that the model has much higher confidence. Now you see it. Whereas for the one that is in red, we see that there's a shift to the left, which indicates that for many voxels, the confidence is lower. Here, by the way, we see much more overlap between the two distributions, so it's really important. It's going to be very important to use the average to compute the COBRA score. Here, individual voxels are really very noisy. Okay, so now let me show you the diagram that shows how we apply the COBRA score to quantify disease severity in the case of knee osteoarthritis. What we do is, again, we train on healthy individuals for a clinically meaningful task, which is, in this case, knee tissue segmentation. And then we apply those AI models on data of patients that have several degrees of possible knee osteoarthritis severity. Here I'm showing you 3 examples: healthy, mild, and severe. This is a normal knee, so the confidence level of our method is high, which means that the knee is healthy. Here, this knee is mildly affected by knee osteoarthritis, so the confidence goes down, and we determine that the patient has mild knee osteoarthritis. And here, this knee is severely damaged, so now the models are not able to perform segmentation with high confidence. The confidence goes even further down, and then we determine that the knee is severely affected. Again, it's very important that we compute this score as the mean or average of the confidences for all the voxels in the magnetic resonance scan, and this gives us a stable, accurate metric, as opposed to using individual voxels, which would be extremely noisy, as you can see from the overlap of these two distributions. So in this case, we get a COBRA score of 0.864 for the healthy individual and a COBRA score of 0.781 for the individual that has an impaired knee, that has a knee osteoarthritis severity of 4. Notice that this is the other way around than with stroke. So we're going to see an inverse correlation between the COBRA score and then the Kellgren-Lawrence grade, because here the higher the Kellgren-Lawrence grade, the higher the disease severity. So these are our results. Our test cohort in this case contains 435 individuals that range from healthy all the way up to severely having severe knee osteoarthritis as quantified by the scale or Kellgren-Lawrence grade. And here we're seeing the COBRA score of each individual patient and also a kernel density estimate of the density of the COBRA scores. And what we observe is that, again, we have a strong correlation, in this case inverse correlation, between the expert-based traditional score and our automatic score, which is computed exclusively using machine learning models that were trained on these healthy individuals. And again, the results are statistically significant, as indicated by these 95% confidence intervals. Okay, so now we've reached my concluding remarks. So what we have seen in this work is that our COBRA framework enables us to perform anomaly quantification using AI models that are trained exclusively on healthy patients. And we have verified that this achieves high correlation with expert-based metrics for two very different medical conditions, stroke and knee osteoarthritis, and three very different data modalities: video, wearable sensor, and magnetic resonance imaging scans. Lessons learned from this, and which could be applicable perhaps in other situations, is that model confidence can be very informative about deviations from normality as long as you average. Also, auxiliary labels, highly granular labels describing a subject, can be extremely useful even if you only have them for healthy subjects. Realize that in our work we don't need labels, motion labels for the stroke patients. We don't need tissue labels for the knee osteoarthritis patients. We only need them for the healthy subjects, which might be easier and cheaper to obtain. Now I'm going to get to the part where there's a word of caution. For one of the activities that we used in our stroke application, the activity involved an object which sometimes was highly visible for some of the patients and sometimes was dark and very difficult to see. And I want to emphasize that our COBRA score, our video-based COBRA score, is using all rehabilitation activities, okay? But now for this instructive word of caution, I'm going to show you what happens if we compute the COBRA score only based on this tabletop activity where they're moving this object around. And what we see is that when we compare the COBRA score with the FMA score, and again, this is a COBRA score that is computed from videos and only for this activity, we observe that if we look at the individuals that had a light-colored object, which are indicated by these light markers, and we compare them to the individuals that had a dark-colored object, we observe a systematic loss in confidence only caused by the object color. I realize that this object is difficult for us to identify as humans. I mean, you can barely see it, it's right here. So it's also going to be difficult for the machine learning algorithm. And that causes a systematic loss of confidence that has nothing to do with impairment. It's a confounding factor in that sense. And because of that, for just this task and just using the video data, we observe a lower correlation between the COBRA score and the FMA score. This doesn't happen for our general COBRA score because we use many different activities, so this doesn't affect things as much. You could also think of situations where you really need to use this activity, and in that case, what you would try to do is identify these confounding factors, and you could adjust for them by grouping the data, stratifying the data in causal inference lingo, according to the confounding factors. So here we group only the patients with dark-colored objects. We observe a higher correlation with the expert-based score, and if we do that for the light-colored objects, the correlation is actually much higher. This also kind of hints at not using these dark-colored objects that produce uncertainty in the output of the machine learning model. So the word of caution here is that there could be confounding factors that produce a spurious loss in correlation, which would then not be associated with impairment or disease severity. We have observed that this can be addressed by using an heterogeneous data. In the case of the video-based COBRA score for stroke, we use many different rehabilitation activities, so this was not a big deal because of that. And also, you can correct for it via stratification as long as you actually identify the confounding factor. And that's all I got. If you want more information, I'll refer you to our 2 articles on this method, and also to our previous articles on performing motion detection, motion identification for stroke patients. I cannot end without thanking my co-authors who did all of the work here. This is Boyan, who is a PhD student, sorry for the delay, who is a PhD student at the Center for Data Science. This is Akash, who used to be a PhD student at the Center for Data Science and is now at Google. This is Kaneng, who also used to be a student at the Center for Data Science and is now at Adobe. And this is Rajesh Ranganath, who is still at the Center for Data Science. He's faculty, he's in computer science also, and is a co-supervisor of Boyan. This work definitely would not have been possible without the vision of Heidi Schambra, who led this work on the clinical side and runs the Mobilis lab at the NYU School of Medicine, and also her group. And finally, I would like to acknowledge the support of NIH and NSF, without whom this would not have been possible. All right, thank you very much for your attention.